So thank you very much for that lovely introduction, and now you've set me up for a hard challenge. It's wonderful to be here. I'm very grateful to have been invited, and I'll begin my talk, but I'm open to questions, and so if as I'm speaking something's not clear or you have a question, feel free to flag me down. If the questions get to be too many, I'll move us along. Okay. So my research starts from the observation that human infants grow up in very busy social environments. They're surrounded by the actions of other people. And their ability to thrive in this social environment, to learn from it, and to be successful in it, depends on being able to perceive the important structure in this very complex social environment. And for much of my work, I've focused on what I think of as an important foundational element of the structure in the social world. There's actually lots of complex structure in the social world, and I've spent 20 years or so thinking about one piece that I think is important and foundational, and that is the idea that when other people move around, they're not just physical bodies in motion. They're agents whose actions are organized with respect to goals and objects of attention. This idea is sometimes talked about in terms of what's called intentional relations. The idea is that people are connected to, people's actions are connected to and directed at things in the world. So for example, in this picture, you see a little boy and his mother. And it should be obvious to you that the boy is paying attention to something. And you don't know what he's paying attention to, but you know about where it is. And the fact that he's paying attention to something is as real to you as are the stripes on his shirt. You don't have to think hard about it. It's an obvious piece of this scene. And it's an important piece of this scene, probably more important than the stripes on his shirt, right? So I'm going to call that ability that you all have when you look at this picture and you understand that these are two agents who are connected to each other and to entities in the world. I'm going to call that intention reading. And what I mean by that is the understanding that actions aren't just movements through space. They're structured by goals and objects of attention. This aspect of social perception is a conceptual building block in a couple of senses. First of all, it's sort of in our online engagement with and analysis of information in the social world, it's an important information processing step. If we have to represent others' actions in terms of their goal structure or intentional structure in order to be able to do much else in terms of social thinking and social responding. So sort of in the moment, it's foundational. It also turns out to be developmentally foundational. So I'm going to talk about a bunch of studies that look at infants' understanding of this aspect of action. And it turns out that infants' performance in these studies, not in my work but in other people's work, predicts their later theory of mind. We heard about theory of mind. Their later explicit understanding of the mental lives of other people. So it suggests that this aspect of social perception, which I'm going to tell you emerges early in life, is also developmentally foundational. Okay. I put this quote up here, and you can all read it well, just to point out that we could perceive social scenes differently. So it's tempting to look at that woman and her son and think, well, it's obvious. There's no other way to make sense of this scene except that you've got two intentional agents, looking at things and connected to each other. And there's this wonderful quote from Alison Gopnik and Andy Meltzoff and Pat Kuhl that describes a very mundane scene, but in terms that make it clear that there's other ways to see the social world. So they write, this is a family around the dinner table. Take the people around the table. We seem to see husbands and wives and friends and little brothers, but what we really see are bags of skin stuffed into pieces of cloth and draped over chairs. There are small, restless black spots that move at the top of the bags of skin, and a hole underneath that regularly makes noises. The bags move in unpredictable ways, and sometimes one of them will touch us. It sounds horrifying, right? Okay, so this is just to sort of make it clear that this perception that we have of others as intentional agents, although it's automatic and very intuitive to us, is actually an act of inference, right? It's an important kind of structure that we place on the social world. Okay. Turns out, developmentally, the ability to Understand other people's actions is an important foundation for lots of kinds of social learning. So there's decades of research showing now that when children learn language, they filter their learning through an analysis of what other people are intending to do with the words that they use. They're not just somehow mapping words onto things that are around when they hear them. They're trying to understand what people's communicative intentions are. Similarly, when babies are engaging in what's called social referencing, they're learning what's safe in the world or what they should approach. That learning is also informed by an analysis of the intentions of the people who are producing the emotional signals that might be informative. And when babies are imitating other people's actions, which is a very important aspect of learning in life, acting like a member of your cultural group. Similarly, babies learning in imitative contexts is filtered through their analysis of other people as intentional agents, right? So it's there relatively early in life. And I thought I brought a video that's not from my research. It's from the research of Felix Varniken, who's at Harvard now, and Mike Tomasello. It's a video of a baby, about an 18-month-old infant, who's being helpful. And I just want to show it to you so you get a sense of the way in which thinking about other people's intentions is probably related to early social competence. This is Felix Varniken. This baby watches, thinks about the problem, and then figures out what to do.
So?
Okay, so it's absolutely charming. And so what Felix and Mike have demonstrated is that young, typically developing children have this spontaneous tendency to want to help. They think when they're watching people act, they're thinking about what's that person trying to do, what's his goal. And one piece of evidence that they're doing this is their spontaneous ability to figure out good ways to help someone in distress. So, interestingly, in this experiment, each baby had one scenario like this, so one trial. And you might ask, how many babies do you have to test to see behavior like this? It's relatively common. So I can't remember exactly what proportion, but a sizable enough proportion of the babies did something like this that they could report it as a finding. So somewhere between 14 and 18 months. Yeah. Did you have a? About 14, 18 months.
When was the earliest that was seen?
So that's 14, 18 months, somewhere in there. There's good evidence for this. Okay. So today what I want to talk about, we have evidence that by the time babies are in that second year of life, they're engaging in thinking about other people's goals and acting, and it's supporting lots of their important social learning. So I'm going to talk about what happens before then. What are the origins of this ability early in infancy? So when do infants begin to engage in intention reading? And I'm going to talk about two ways we've looked at it. One is, what's the earliest we can find any sensitivity to other people's goals in acting, and we use very sensitive methods to try to get at that. And then more recently, we've been doing some work looking at when can babies recruit this analysis quickly enough that it might be useful to them in a social interaction, right? Because of course social interactions require not only that you can think about what somebody's goal is, but that you can think about it fast enough to respond appropriately. So we've been looking at sort of the time course of infants' use of goal information. So having talked about, given you some examples of our work there, I'm going to turn to this hard question, which is, once we know that infants are engaging in intention reading, what are the processes that give rise to it? Where does it come from developmentally? And there I'll talk about some work we've done looking at different kinds of experience in driving infants' intention reading, two kinds of experience. One is, that we heard about in the introduction, infants' own experience as agents controlling their own goal-directed actions, and another kind of experience which is engaging in joint collaborative actions with other people. Okay, so here's the question I asked. You see this woman. You don't just see a woman with her arm outstretched, right? You see somebody who has a goal. You see she's reaching for that dinosaur. And the question we wanted to ask when we began this research is, how do infants see this? What do they think is going on here? Do they see a woman with her arm outstretched, or do they see an agent whose actions are organized by a goal? Okay, so I wanted to ask that question of people who are like this, right? Pre-verbal infants. So there's a limited set of tools you could use to ask a question of somebody who's an infant. And the first tool that I used, and since I know that Liz Spelke was here recently, some of you might have heard about some of her work. The first tool that I used to address this question was the visual habituation dishabituation paradigm. And what you do in a visual habituation experiment is you show a baby an event again and again and again until they get tired of looking to it, till their looking declines to some criterion. And then you make a change in the event. And babies, once they're habituated, will look longer at a change so long as they detect the change and think it's an important change. So in one study, for example, I think I have a pointer here. These are studies that we've done with babies as young as 5 to 6 months of age. So what I'll tell you is true for babies at 5 to 6 months of age and under some condition by 3 months of age. We show babies an event where a person reaches through space to grab a toy. In this picture, the arm, she's reaching and grabbing a teddy bear. That event has a relation between the goal and the object. You'd talk about that. That's how you'd describe it verbally. You'd say, she grasped the bear. That's the important part of the event to you. But it also has lots of spatial properties. The arm moves through space to a certain extent. It has a certain angle when it's done. You can see a certain amount of the arm when it's done. So there are also sort of movement properties of the event. So once babies are habituated to this event, what we do is we reverse the position of the toys, right? And that enables us to show babies events that either change the relation between the agent and her goal, so we call those goal change events, or change the movement properties of the event, but preserve the relation between agent and goal, right? And we can use babies' length of looking or attention to changes in the goal versus changes in the sort of movement properties of the event to figure out how they saw it. If they saw that original event in terms of the relation between agent and goal, we should see a big recovery in their attention on new goal trials. If instead they focused on the spatial properties, we might see a big recovery on new side trials. I didn't bring a data slide, but I'll just tell you what the findings are. In many studies, some of them are cited there, what we find is that babies look longer on new goal trials. When the goal changes, you get a big recovery of attention. When other properties of the event change, but the goal remains the same, you don't get any real recovery at all. In fact, babies don't even recover from where they're looking at the end of habituation. So this new side event is perceptibly different from the habituation event in lots of ways, but it's still, she's grabbing the bear, and babies see it as pretty much the same thing as what they've been seeing all along. Okay, so this method has been used, one thing I want to point out is in various control studies and control experiments, we have put into the event, instead of an agent moving, doing sensible things, either an inanimate object that moves through similar paths or an agent doing ambiguous or apparently accidental things, like dropping their hand on top of the toy. And what we find here is these events are matched to reaching events in terms of their timing and the trajectories of movement, but babies see them very differently. And so across the studies, it looks like infants' intention reading is selective for the well-formed goal-directed actions of agents. These findings are important for a couple of reasons. One is they give us some more certainty that what we're seeing in the case of the reaching condition has something to do with understanding the intentions of agents and isn't due to some other factors in the event, lower-level factors. But it also tells us that babies are pretty good at recognizing agents and figuring out what constitutes a good goal-directed action quite early in life. Okay. Across the first year or so, we see a kind of emergence in the kinds of intentional relations, the kind of intention reading that babies can engage in. So by 6 months for sure, and possibly earlier, babies see grasping events as goal-directed in terms of the relation between agent and goal. A bit later, between 8 and 12 months, they see acts that happen at a distance, like paying attention to something, looking at something, or pointing to it, as involving that same kind of relation. Also, toward the end of the first year, babies can begin to think about more abstract kinds of goals, and I'll show you an example of that in a second. But imagine that very often our intentions are distributed across multiple actions. So for example, the woman in this picture is pulling on a blue cloth, and what she's going to get, having done that, is this yellow duck, right? So really, she's got a kind of higher order plan, something like pull on the cloth to get the duck, right? So you see her actions on the cloth as directed not at the cloth itself, but at the duck. That's a kind of higher order goal. By about 12 months of age, babies can recover goals like that from other people's actions. You can also distribute higher order intentions across people, so you can have two people that have the same goal. Like here's a woman in red who's opening this box so that the woman in blue can get the toy out that's inside it. And they have a kind of shared goal, which involves getting the duck out of the box. And by 13 months, babies recover that kind of goal structure from events. Okay. I wanted to just show you quickly an example of how we know babies can recover this higher order goal structure. So here's a study I was done with my student Jessica Somerville some years ago. And we showed babies events where a person pulled on a cloth to get an object. And we wanted to know whether babies could think about the fact that she's got this higher order goal, so that when she's pulling on that cloth, it's not really the cloth she wants, but the toy that sits on it. And what we did is habituate infants to this sequence. She pulls the cloth and gets the toy. And then following habituation, we reverse the toys. So we put the green thing on the blue cloth and the red thing on the yellow cloth, right? And that allowed us to show babies two kinds of test events. In each of them, she just grabbed a cloth. In one, she grabbed that same cloth she'd been acting on in habituation, but now it supported a different toy, right? And in the other, she grabbed the other cloth, which supported the same old toy. And we sort of were asking babies, what do you think this contact with the cloth is about? Is it about the cloth, or is it about what the cloth might get you, right? The downstream goal. And what we found is that by 12 months, babies look longer on new toy events than new cloth events, right? Suggesting that they're not just thinking about her relation to the cloth. They're thinking about the downstream goal associated with getting the cloth. Interestingly, they're doing something more sophisticated than just thinking about the order of events, right? You could think, you think every time you touch the cloth, you get the toy. So there's a kind of linear connection there. But if we change the events just a little bit, we take the red toy off the cloth and put it next to it. Now she pulls the cloth and gets the toy, but there's no causal structure there, right? It's not that pulling the cloth enabled the getting of the toy. Now the effect goes away. So it tells us that babies are actually thinking about how people's intentions interact with the physical world, thinking about the causal constraints in a situation to figure out what somebody's intentions might be. Okay. Questions? Okay. All right. So all of the data I've been summarizing kind of briefly here comes from looking time, habituation experiments, where we show babies an event again and again and again until they get bored with it. They can stare at it as long as they want. Once they look away, we decide they're bored with it. They have a very long time to think about the events that they're seeing. And under these quite supportive conditions, we find that pretty young infants are recovering goal structure from other people's actions. But as I said at the beginning of the talk, an open question is when and whether babies can do that kind of analysis quickly enough that it would be useful to them in a social interaction, right? To be socially useful, our analysis of other people's goals has to happen quickly. In a conversation, if there's a delay of even half a second before one participant responds to the other, the whole thing falls apart, right? You've got to be quick. Think about that baby who had to watch Felix for a while before knowing that they should go help, right? If Felix hadn't been doing an experiment where he continued to try until the baby helped, the baby probably would have missed his chance to show what he knew, right? So we've been using eye tracking, remote corneal reflection eye tracking, to try to get a sense of the time course of infants' analysis of other people's goals and figure out when and whether babies could do this fast enough to look smart in a social interaction. Okay. So I'm going to show you an example video in a second. But the logic we use in the experiments is really similar to the habituation experiment. There's two toys and there's a person. And a person acts on one of the toys. And then we switch the toys' locations. And then the person begins to act. And what we look for is a prediction. Where does the baby think the person is going to go, right? So I'll show you an example and talk you through it. This is a video that's generated by our eye tracker that shows the stimulus event that the baby was looking at, and then there's a red dot, and the red dot is where the baby's looking, the point of fixation on the screen. So you can see where the baby's attending. By the way, parents love participating in these experiments because we play this back for them at the end of the session, and they think they're seeing into their baby's mind. You have this strong sense that you know what your baby's thinking. Okay, so I'll show you, and I'll just sort of talk you through it. Okay. A little sound. This is just to get the baby paying attention. There's the baby's fixation. Okay, now there's just a couple of setup events so that the babies get used to there's somebody, there's a woman, and she's reaching for things. And you can see they're following that. They look at her, they look at the object, they watch her reach. Okay, now the critical setup event is going to happen. There's going to be two toys, and she's going to reach for one of them. It's going to be that little bear. Okay, she's reached for the bear. Okay, that's the setup. Now here's the test. The toys are in different positions. Her hand comes up. Baby looks at the hand and looks at the bear. Did everybody see that? Okay, I'll stop it. So that's the predictive behavior that we're interested in. So once the baby looks at the hand, do they predict that the hand is going to go to the same toy, or do they predict that the hand's going to move back to the same location that it's been going to? Okay. Just to give you a little bit of information about how we collect data from this. So we look at what's called regions of interest. So there's the woman's hand, the woman's face, the two toys. I'm going to tell you about two kinds of data we pull out of this. One is what we call predictive fixations or predictive looks. So we look at once the hand comes up, if the baby's looked at the hand, what's the first thing they look at? Do they look to the prior goal, or do they look to the prior location, right? And then, because we're interested in how quickly babies do this, we also just look at latency. How long does it take them to generate that prediction? Okay. So first I'll talk about the overall patterns of predictive fixations. Okay. So these are data from a couple of experiments with babies between 11 and 15 months of age. The top two examples here are from the study I showed you, so where a woman's either grabbing a toy, or in a control condition, she's looking at and laying the back of her hand on the toy. And we know that babies aren't real sure what you're up to when you put your back of your hand on something. And what's plotted here is just of all the predictive looks they made, the proportion that were goal predictions as compared to location predictions. And in that condition with the graph, you see that babies are reliably above chance in generating goal predictions. In the case where she's putting the back of her hand on this thing, they're actually right at chance. So that tells us that babies are, in the context of this event, thinking about the details of how she's acting on the object and using that information to inform their predictions, right? We have a similar kind of, this was a set of studies where babies just saw the hand, and the hand reached for one of the two toys, or there was an object, a mechanical claw, that moved in and made contact with one of the two toys. And here again, we see that babies, in the case of the hand, reliably generate goal predictions. Interestingly, in the case of the claw, they're below chance, which means that they're reliably generating location predictions. They have ideas about what objects should do. Objects should move to the same place they moved before. Hands should move to the same goal they moved before. Okay. So these findings are telling us that babies by 11 to 15 months of age are able to implement their intention reading in the moment, more or less. They're able to predict in the context, in the time frame of the events you saw, what the woman's going to do. Okay. But when we look at the latency data, we see something kind of interesting. So these are just latency data from 15-month-old infants in the stuffed animal event that I showed you. And what we look at, well, babies on average generate goal predictions, but they're babies. They don't always do it. Sometimes they generate location predictions. And so what we looked at was how long it took them to make a goal prediction versus how long it took them to make a location prediction. And what we found is that it actually takes them longer. It takes them about 3 seconds on average to generate a goal prediction, and much shorter to generate a location prediction. And here's how we interpret that finding. Making a goal prediction is hard. It requires that you recruit some analysis of the person's actions in order to generate the prediction. And that cognitive effort is expressed in babies in a longer latency, in a delay. A location-based prediction is just moving your eyes back to the same place you moved them before. No real thinking is involved there, right? So that's fast. It's fast and dumb versus slow and smart, right? Okay. So this finding is suggesting that, yes, babies can generate online predictions, but it's hard. There's effort there that actually makes them slow, right? And that finding made us realize that we might be able to explain a kind of puzzling paradox that's been around in the literature. So my data from visual habituation experiments, along with other folks' data, suggests that babies are socially smart from very early in life. Data from Mike Tomasello's lab and other folks' labs that look at social interactive measures of social intelligence suggest that, in fact, babies are not all that smart until they're, over a year. So there's this kind of discord that initially expressed itself in terms of people doubting whether other people's data were real, and then expressed itself in terms of people thinking there must be some trivial explanation for the other person's data. But now I think we actually have a satisfying answer, which is that maybe young infants can come up with the right analysis given sufficient time. And what's changing over the course of the first couple of years of life is the rapidity with which they can generate that analysis. So if that's right, then we should be able to see a relation between how quickly babies can generate goal predictions and how socially competent they look, right? So I'm going to tell you about a study we did to look at that. We tested a group of 20-month-old babies, and we tested them in that eye tracking task that I showed you that had the teddy bear and the giraffe in it. So we got for each infant a goal prediction latency, how long it took them to generate a goal prediction. Each baby also participated in a social perspective taking task. So this is a task that's pretty hard for 1.5-year-old children. There's a woman, here it's depicted here. There's a woman and there's 2 identical toys, 2 cars. One of the cars she can see. The other car she can't see, but the baby can see both cars. And she sticks her hand out and she says, "Can you give me the car?" So that's an ambiguous request, right? If you're tuning into what you can see and able to use that information quickly to interpret what she's asking you, then you'll know that she must be asking you about the car she can see, not the one she can't see, right? So that's the display, and this is a baby responding, in this case with apples, giving her the apple she can see. As a group, 20-month-olds are random in this task. It's a hard one for them. Okay, and what we looked at was whether their propensity to be right in the perspective taking task was predicted by how quickly they could make goal predictions. And the answer is it is. So babies who make very fast goal predictions, so that's on the x-axis here, are more likely to be right in the perspective taking task. That's what's on the y-axis at 20 months. And that relation holds when we control for the age of the infant, how attentive they were during the procedure, and even when we control for their understanding of the words in the task. Do they know apple? Do they know car? Right? There's a version of the perspective taking task where there's 2 different toys, and the woman asks for the one she can see. So those are known label toys, where just your knowledge of the word will help you get the right answer. And when you control for children's performance on those trials, we still see this relation. Yeah?
What do you think's happening with the 3 yellow squares on the car?
I don't know. Right. So these are babies who really never got it right, right? Despite the fact that they had some variability in how quickly they predicted. I don't know. Yeah, right? It's one possibility is that there's something interesting about those 3 babies, right? Another possibility is that there's something pretty uninteresting about those 3 babies, right? Maybe they had a strong hand preference. Maybe they didn't like the woman who was talking to them. Maybe they were, I don't know. So it's hard with infant data to be really sure. But it would be interesting to try to figure out if there are some stable individual differences that look different in this kind of task. Yeah. Okay. So infants are socially smart, right? We can see a couple of ways in which they're smart. When babies are young, we see a kind of ability to analyze others' goals when you have a fair amount of time to do it. So when you have time to stare at a scene, you're able to work out what the intentional relations are in that scene. You see that in young infants. And in slightly older babies, beginning around 11, 15 months, we're beginning to see the emergence of the ability to implement this analysis quickly in the context of potentially in the context of social interactions as a person's actions are playing out. Okay. So I'm going to turn now to the second piece of my talk, which is, given that babies are socially smart and we can measure their social intelligence in these various ways, where do these abilities come from? What are the origins? And so if some of you heard Liz Spelke talk recently, you'll be familiar with one kind of argument about infant cognitive abilities, which is the assumption that if little babies do something that looks kind of intelligent, it must be because there's something innate, right? There's some innate conceptual ability that's driving their performance. Most often what people mean by the word innate, because it has many meanings, but what people mean by the word innate when they make these claims is that babies didn't learn how to do this from experience. Instead, somehow they come set up to be able to do it, right? In much of my work, I've asked whether that's really the case, and I've looked hard at whether experience of one form or another might actually be driving these very early acts of intention reading. In part, I'm motivated by the fact that there's pretty good evidence that something is affecting, some aspect of experience is affecting infants' abilities. And that is that things change. So I've showed you briefly the idea that things change. So infants' ability to recover goals from events undergoes this kind of emerging complexity over the first year of life, where little babies seem to know what's up when people are reaching for things, but not when people are looking at things or doing complicated means-ends actions. And by about the end of the first year, you're beginning to see some sensitivity to those more complex or abstract kinds of actions. And there's also, I just showed you what looks like maybe change in terms of the second piece, the ability to rapidly recruit goal analysis about other people's actions, right? Suggests that maybe babies are becoming able to do it more rapidly over time as they get older. And so the piece of experience I got interested initially in looking at this, was the experience that babies get from being agents themselves, okay, from their own actions. In part, this was motivated by the observation that there's lots of what's called species-typical abilities. These are abilities that a species has to be able to do to survive. They're clearly, in some sense, an evolved capacity, right? But in many species, these species-typical abilities depend on experience. So a bird learning its song, for example, right? Or a duck learning who to imprint on. Critically depends on experience to emerge. And so we could think about, well, what are reliably present aspects of a human infant's experience? And one thing is that they're agents. They do stuff, right? Interestingly, very often these species-typical abilities in other species depend on experience that's generated by the animal itself. And so this kind of a neat example, potentially, of humans doing that. I'm going to actually talk about two potential sources. So information provided by infants' own actions and information provided by interacting with social partners. That's another thing that all human infants who end up surviving do, right? If human babies aren't with social partners, they don't live. It's a part of their environment. Okay, so let's talk about the infant's own actions. For a long time, over 100 years, people have thought understanding other people's intentions is hard, and the fact that you have intentions yourself probably helps you with that in some way, right? That's been around for quite a while. And thinking mechanistically about this could happen, how this could happen, there's at least two, they're not mutually exclusive, they could happen together, ways in which this could happen. So one is that there might actually be shared neurocognitive representations that are there for controlling your own actions and do some work for perceiving structure in other people's actions. And there's a fair amount of evidence that something like this is true, although almost no evidence for human infants. And so all the thinking that goes around with respect to mirror neurons has something to do with this. But it's also the case that your own actions can serve as a kind of example from which you can make analogies. So if you know something about what you're doing, you might be able to use that information as a base for analogical projection and understanding what other folks are doing. I actually think these two are, although you can state them as distinct, I think they're not distinct. And I can talk more at the end about why I think that. But okay. I want to point out, since you're probably not all infancy researchers, that in fact, infants' own actions have structure in them that could be informative with respect to the goal structure of other people's actions. And what I mean by that is babies' own actions are prospective and goal-directed from quite early in life. So some lovely examples from people who've studied motor development. So this guy here is Klaus von Hofsten. And Klaus has a whole career of beautiful experiments. And this one, what he has is babies watching as little teeny objects translate through space in front of them. And what babies do is they try to catch the object. And they reach for where it's going to be, not for where it is when they start the reach. So they're thinking ahead to what's the situation going to be when my hand gets to the object. I better aim for that place in space. That emerges very early. Klaus also did some really great work showing that when babies are reaching for objects, the shape of their hand anticipates the thing that they're reaching for. So if I'm reaching for this rod and it's like this, my hand's going to have an orientation that will work there. If the rod's horizontal, my hand's going to have another orientation. Babies do that same thing from pretty early in life. I won't talk about this one. I'll talk about this one. Babies also engage in these kinds of means-ends actions by about the end of the first year of life, where they can see a problem. There's a neat toy. They can't reach it, but it's on a cloth. They can pull the cloth in order to attain the toy. So these kinds of prospective goals organize babies' actions from very early in life. It turns out that those aspects of babies' actions correlate with their perception of other people's actions. So we've done some correlational studies over the years where we take a group of babies who we know in our visual habituation task will be, as a group, random, right? They're too young to show the effect of interest robustly as a group. And we also measure in those infants their own action capabilities. So for example, in this study, we showed babies these means-ends events that I told you about. And we also measured how good they were at pulling a cloth to get a toy. And what we found is, controlling for age and a whole bunch of other important things, babies who were good, they were planful, they were good at pulling that cloth to get the toy, perceived the goal structure in the event appropriately. They thought the red bar is looking at the new cloth event, the new toy event as compared, to the new cloth event. They basically thought the experimenter's actions are aimed at the toy, not the cloth. Babies who were poor, weren't good yet at pulling the cloth to get the toy themselves, actually had the opposite interpretation. They thought when she touched the cloth, she probably wanted the cloth, right? So we can see babies at the same age who are different in their own motor capacities interpret people's actions differently. The same is true for babies who can point and understanding of other people's pointing actions. Okay, so those are correlations, right? They're suggestive, but of course if we want to know whether in fact babies' actions cause a change in their, in fact, causally relate to action perception, we need to do interventions. And so we've done a number of different kinds of intervention experiments where we take infants of a given age, teach them to do something they haven't done before, and then look at the effect that that has on their perception of structure in other people's actions. Okay. The first place that we did this was with 3-month-old babies. And we used something called sticky mittens. So 3-month-old babies, when you show them a neat object, they're not generally terribly good at getting their hands on it. So they'll fixate it, you'll get some movement of the arms, but you won't typically get a well-coordinated, smooth reach, right? They're working on that. They work hard for 2-3 months, and they get to be good at that by about 5 to 6 months of age. Amy Needham, who was my collaborator in the first studies we did here, discovered that if you put really big Velcro mittens on a baby and hold them up in front of toys that have the other side of the Velcro on them, they first kind of swat, move their arms, and then they accidentally apprehend one of the objects, and they notice what they've done. And then if you take the object off and put it down again and let them do some more swatting, they start to get more organized relatively rapidly. It's extremely reinforcing for them. These are babies, when you're 3 months, there's not a lot in life you can control. You put these mittens on them, now they can control something. It's quite exciting. Their eyes get big, they get tense. The parents try to steal the mittens on the way out of the lab because they're so much fun. So Amy was developed the mittens in the context of understanding what babies learn about objects from exploring them. Amy and I got to talking and decided it would be interesting to see what would happen if we gave babies mittens practice and then looked at their perception of actions. Would engaging in mittened actions change how they saw somebody else's reaching action? So we tested one group of babies where they had active experience using the sticky mittens, and then in later experiments we've had various kinds of other control groups of babies. The most interesting one is this group of babies who gets to observe an adult using a mitten to move things around. So they have all the same kinds of visual experience, but they don't actually get to enact the action themselves. We actually did these experiments in a kind of yoked design where we use the actions of inactive babies to generate a script for every baby in the observational condition. So they had really parallel kinds of experiences, but the only difference being that babies themselves didn't produce the action. And following these training experiences, we test babies in that habituation procedure that I talked about at the beginning of the talk, where we're looking at whether babies encode reaches as being about the relation between the agent and the object. And what we find across several studies is that this active Mittens experience leads to this big recovery to a change in goal. That's kind of our signature for what it means when babies have seen something as goal-directed. But observational experience has no effect whatsoever. So even though babies are seeing mittens and seeing mittens that act on toys, they don't seem to get anything from that experience unless they themselves have been the ones who use the mittens. We did that same logic in the context of training slightly older babies, 8-month-old babies, to pull claws to get toys. So 8-month-old babies as a group are not all that good at means ends. If you set up a problem, there's a thing they really want, it's on a cloth, and they could use the cloth as a means to attain the toy. Most 8-month-olds won't come up with the right answer to that problem. They might strain at the toy, they might play with the cloth, they might get frustrated, but they're not so likely to pull the cloth and get the toy. But they're trainable. I'm going to show you an example of what that looks like. And so our question was whether training babies to pull a cloth to get a toy would change how they perceived these events in the habituation booth when they saw somebody else pull a cloth. And again, we had a matched observational control. I want to show you what this looks like, in part because it's cute and we need a movie, but also it gives you a sense of how it is that babies are organizing their actions. So this is an 8-month-old baby. You're going to see that what we do is initially present her with this cloth pulling problem, and she's not really going to know what to do. Then you're going to see we do a little bit of training, and then you can see what happens. Okay. So there's the problem. This is the first time she's seen it. Uncertain. There, now, I guess I'll play with the cloth. That's what we have to do here. Right? And then at the very end, she goes, there's a duck there. But unfortunately, the duck falls on the floor. Okay. So that's a common kind of thing for an 8-month-old. Now this is what training looks like. We just show her what you ought to do here, and then we immediately give her a chance to do it.
See that again?
The experimenter sets up the problem.
Very interesting. Now it's your turn.
Okay, and now it's the baby's turn. Think about it for a minute. Think about what she did. Now what to do, right? Okay. Great. So she gets a few training trials like that. And then in the post-test, we just put the problem in front of her. She doesn't see the model. Brand new problem.
Toys that we're using before.
And then she, right? So at 8 months, it looks like about half the babies we see are ready to do this kind of learning. So she was one who learned, very clearly. The other half of the 8-month-olds we tested never got to this point. So they'd watch with interest, but never quite be able to organize their own actions. And it turns out that mattered for what happened in the habituation task. So it's a little bit of a big graph here, but if we look at babies who got active training, the most planful babies are the top half of the babies we tested, the ones who look like the little girl you saw, who got to be good in their own actions. And when they saw those habituation events, they showed this heightened attention to the change in ultimate goal. So they know when this woman grabs the blue cloth, she wants the thing that's on it, not the cloth itself. Babies who went through that same training and didn't really learn anything from it, didn't have anything to carry forward when they were watching the woman's actions. Okay, so it matters. Their motor learning matters, and their success matters. And babies who got observational training no subgroup of them that we could find anywhere benefited from that experience. So we could look at them as a whole. We could look at babies who saw the most examples in their training, the babies who saw the fewest versus those who saw the fewest. We just couldn't find any evidence that having watched these examples helped them. So again, it looks like doing it yourself matters. Okay. This one I'll just do briefly, but so we have another series of studies that looks at what babies think about these collaborative goals, where these two people, the red shirt lady and the blue shirt lady, are working together to get the duck out of the box. Do they understand that these two women have the same goal even though they're doing different things? It turns out there's a transition, so at 13 months, babies as a group tend to get that. Younger than 13 months, they tend not to. If we take 10-month-old babies and we let them engage in a collaborative interaction with the experimenter themselves, now they understand it. If we have 10-month-old babies and they watch two people collaborate for a while before they go into the habituation booth, they don't get it. So it seems to be something about doing it yourself gives you information that you can carry with you to make sense of other people's actions in other contexts. And just watching other people act seems not to give babies that same kind of knowledge. Okay. So these are all studies that use that visual habituation paradigm. And across them, we see that active experience supports infants' intention reading for reaching for things, means, ends, actions, and collaborative actions. Does active experience also affect babies online, sort of their ability to rapidly recruit this goal analysis online? So we've just begun to ask that question. And we've done it with 8-month-old babies. So I'll just tell you at the outset, we also tested a group of 8-month-old babies in those eye tracking studies. And as a group, they don't do anything systematic. Okay. So we thought, well, what happens if they get to do some reaching for things first? So we took one group of 8-month-olds, and we just let them do this before they went into the eye tracking experiment. Yeah, simple, right? These are babies who can reach for things. They're 8 months old. They're pretty good at reaching. So we're not teaching them to do a new action, but we're priming their motor system. We're getting them engaged in doing, right? Okay, and he's very cute. Okay, so we had one group of babies who did the eye tracking procedure with no prior training, another group of babies who did it having first reached for things. We did the same analysis looking at predictive fixation, so did they, on the whole, tend to make goal predictions versus location predictions, and then we looked at the timing as well. So this is what they did on the whole. This is the data I told you about earlier, just plotted slightly differently. Plotted here are the number of goal predictions and the number of location predictions. So 15-month-olds are making many more goal predictions than location predictions. 8-month-olds without training are equally likely to generate the two kinds of predictions. And 8-month-olds with training look like 15-month-olds. They're making goal predictions. Okay? Suggests that sort of revving up your own action system might do some work for helping you reason about other people's actions in the moment. I think most interesting is the latency data. So remember I told you that for 15-month-olds, it takes longer. They're thinking harder when they're making a goal prediction, right? And we see that expressed in their latencies. Babies, 8-month-olds with no training, are kind of equally quick. They're being fast and dumb, right? Not thinking hard. But after training, we induce this latency difference. It's as if engaging in action is getting 8-month-olds to think a bit harder about the actions they're watching in others. Oh, I have to tell you about this caveat, of course. This is ongoing work. We've finished these conditions. We're in the middle of running an observation condition, so we don't actually know whether it's acting yourself that matters the most in this study. And we should know in a couple months, but I don't know enough now to tell you. Okay, so infants learn about actions from their own actions. Engaging in concrete actions supports insights into sort of abstract aspects of other people's actions, the intentional structure behind other people's actions. Simply watching other people's actions doesn't seem to give the babies the same revved up portable knowledge that they get from acting themselves. Okay, I have about 2 minutes, so I'm going to talk really briefly about the last piece. So over the years, we've gotten all this information that babies are learning a lot about acting from their own actions. And all this time, we've been really worried about something, which is that to be socially competent, you have to be able to make sense of stuff you haven't done yourself, right? It seems pretty obvious. You have to take whatever it is you learn from your own actions, if that's where you're going from, and generalize it really broadly. Understand that when I do something that's goal-directed in this context, it could be a lot like what a concert pianist is doing when he does actions that I myself have no hope of controlling, right? And so how is it that, maybe infants' own actions are only useful for generating knowledge about particular actions, and they have to rely on something else for making sense of other people's novel actions. But we thought, maybe not. Maybe infants' own actions can provide something like a base for analogical extension. We could sort of see how their familiar actions might be similar to the unfamiliar actions of another person. And my student Sarah Gerson and I have been looking into this. So the idea we're testing is whether first-person action knowledge serves as something like a base for analogical extension that helps you make sense of pretty varied events out there in the world, even as a baby. So here's concretely what we mean. So you could have an infant who knows a lot about what's up when they grasp for things and when other people grasp for things. And that infant may see his grandmother using this tool to pick up the morning paper, this claw. And maybe that baby's never had gotten to use the claw. Is the baby unable to understand what's going on here? Or can they somehow reason that that action is structurally similar to their reaching action and then sort of gain some insight into the goal-directedness of the behavior? Okay, so seeing the analogy between a familiar action and a novel one. Well, we know a lot, actually, in the field of cognitive development about what enables people to make analogies or to see analogies. And so Sarah Gerson and I recruited that literature to generate some predictions about the conditions. If babies are able to make these analogies, there are some conditions that should enable them. And basically, you're able to see an analogy easily if the two things, if the base and the novel instance are right there next to each other, and set up in a way that you can see the structural similarity between them. And that basic principle has been shown to be true in people's learning about verbs, in people's learning of math problems, people's learning about physics. It's sort of across the ways that people learn. If you're trying to see similar structure in two instances, the ability to compare them side by side and compare them in a way that they're kind of spatially aligned with each other has been shown to be really important. Well, Sarah and I thought, well, a situation in which that might happen for babies' own actions is when they're engaged in collaborative or joint actions with another person. So imagine a parent who's using, say, a tool. Maybe grandma picks up that paper and hands it to the baby. Now the baby's own action is coordinated with the tool action. And that might, we think, be a situation where babies could engage in this kind of analogical analysis. Okay, and of course social interactions provide just that kind of comparison context. So across many studies that I won't go into, Sarah said, well, let's take a really hard test case from every study we've ever done. The claw is our control object. It's the thing that babies really don't understand as goal-directed. Can we teach babies, 7-month-old babies, that when people use this tool, they're doing something goal-directed? Babies didn't get to engage with the tool themselves, but what they got to do was act jointly with somebody using the tool. That's what's depicted at the top here. The experimenter took the tool, the claw, and handed the baby a series of toys with it. And what that meant was the baby's own reaching actions were coordinated with the claw action. And that was the condition that we thought would be most informative. We had a bunch of control conditions where babies got to play with the claw, but it didn't hold a toy, or babies got to watch the experimenter use the claw to move things around, but they didn't engage themselves. And our prediction was that it wasn't visual familiarity with the claw, it wasn't seeing what the person did with the claw, it was in particular coordinating your own actions with the actions of the claw that would matter. We embedded these different training conditions in an experiment where our measure of goal understanding is the baby's propensity to act on goals that other people have acted on. And I won't go into detail here, but the idea is you see somebody do something goal-directed toward one of two toys, and then you get to act on it yourself. By the time babies are 7 months or so, if they see something they know is goal-directed, they tend to pick up the thing that was the other person's goal. So we use that goal imitation procedure. There's two toys, so if they're above chance, it means that they're systematically selecting the other person's goal. If they're at chance, they didn't learn anything. Okay, so what we see is this physical alignment, this joint action condition is the only one of all the conditions we've run across experiments that leads babies to systematically imitate the goals of claw actions, right? Lots of other things we can do. Babies watch it, but they don't seem to pull away from that experience and understanding of the person's goals in using the claw. Okay, so babies really don't know what's up with claws, but if you give them just a brief interaction that allows them to engage in an analogical comparison between their own actions and the actions of a claw-wielding adult, they get it. So here we see that coordination, babies' own actions are providing another kind of bridge. Coordinating your own actions with another person's actions can lend insight into the goals of the other's actions. Okay. So that's just summarizing. Action experience shapes infants' intention reading because it allows infants to relate other people's actions to their own. And we see this both in terms of when babies act themselves and take away information from that experience, and in the ways that babies' joint actions can inform their action understanding. And now, this is exciting, not just sort of because it gave us nifty insight into a mechanism that we think is working, but it's plausible that this could be really valuable for infants because joint action is a pervasive experience in infants' lives all the time. People are acting jointly with babies, right? That's part of what it is to be cared for and interact with other humans. So we think it could actually be a pretty big contributor in babies' daily experience. Okay, so I'm going to conclude here. So I hope I've convinced you that when babies look out at the social world, they see one really important piece of structure in that world, and that is the intentional structure of other people's actions. And this ability is shaped by infants' concrete experience as agents themselves and as interactive partners with other people. So there are concrete actions and concrete connections that lead to abstract ideas in babies. Thank you.
So I want to start by saying I'm honored to be here. Thank you. Following Amanda is sort of like opening for the Rolling Stones, so hopefully I live up to this. But Amanda's work has fundamentally shaped this field of social neuroscience that I'm a part of. My work is focused on trying to understand how the human brain accomplishes the tasks that have been so beautifully laid out by Amanda's work. We're at the point where we're beginning to understand the neural basis of, for example, intention understanding. And I want to try to show you some of that work and convince you. And I think we're actually at the point where we can understand and have an appreciation for the importance of that neural circuitry in autism. I think we've clearly, I'll argue, shown that it's disrupted in autism, where we can begin to think about actually intervening in that circuitry and then showing quite a bit of plasticity. And I would argue that there's a path forward here, and I've highlighted identify social functions and their neural and genetic substrates. And what I'm talking about is really the bedrock work that Amanda's done. And I'm going to try to convince you that our next steps are to link individual differences in these underlying neural circuitries and the symptoms of autism, to then begin to, and this is really tantalizing from your talk, translate the basic science into treatment protocols. And so I love this idea of non-obvious experiences, and you alluded to it, for example, in the case of baby ducklings learning what to imprint to based on their own action in the world. It's an example of a non-obvious experience. It took a long time for people to think of that, and they had to think out of the box. What I would argue is looking at something like the sticky mittens experiments and getting ideas for treatment interventions that we can do at a behavioral level that I'm going to hopefully show you might actually alter neural functioning in infants at risk for developing autism and subsequently, because we can identify neural substrates for these social functions. And then when this works well, done in blinded, randomized controlled trials, we can then begin to think about really rolling this out. And what's beautiful, I would argue, about this type of approach, and again, building on the work that you've done, is that you can conduct experiments in humans, watch the outcomes, and conduct them on a fairly large scale using very sensitive biomarkers of treatment outcome. And so we start, I always show this slide when I speak, and I've always talked about a social brain that does these things, and social brain. I hope that's an intuitive concept, that we have neural structures that are dedicated to processing social information. What Amanda's talking about is the early development of the social brain, and it's our job as neuroscientists to try to map that out. And I talk about individuating others, perceiving agents, and their actions, down to sharing attention and intentions, which is where we're discussing most of the time tonight. All of these things have their own neural systems. The neural systems come to interact over time, giving you adult, full-fledged social cognition. We've systematically shown that in individuals with autism, these are altered. This was actually an experiment that we conducted early on. It's a brain looking time experiment, and this was very much inspired directly by reading one of Amanda's papers. So focus on one of these at a time. So this is Caitlin, graduate of the University of Chicago. And Caitlin was my lab manager for many years. She's on the job market right now as well. She just got her PhD. So Caitlin, focus on this one. Let me let it run one more time. So Caitlin expresses positive regard towards the red cup, and then she reaches to the red cup. In contrast, so this, I would argue, is congruent. Her intention, she likes the red cup. If you're trying to figure out what Caitlin might do, she'll reach to the red cup. It's consistent with your expectations. You need an expectation to understand an intention. Positive incongruent. Caitlin likes the red cup. She reaches to the green one. This is an event that a smart baby would look longer at. Down here, just mixing it up a bit with the emotion for control. She dislikes the green one. She reaches to the red one. That's congruent. She dislikes the green one and nonetheless reaches to it. Then that's incongruent. So completely inspired by the studies of babies. But in this case, we wanted to know which neurons look longer, and as revealed by functional magnetic resonance imaging, and in adults. So what we found was that this region of the right posterior superior temporal sulcus responded much more strongly when an adult subject watched an incongruent action relative to a congruent. And an important point to make here is that this is a system you can't turn off. So no matter how many times you see Caitlin looking to the red or the green cup, your posterior superior temporal sulcus continues to process the congruency or incongruency. It's sort of a slave to doing this. And so this is something that you don't ponder. Maybe the first time you see Caitlin, you think, what's Caitlin going to do? After that, you're bored out of your mind. We have to pay people a lot of money to sit in the magnet and do these studies. So it's the same thing over and over again. But what's critical is to point out that I think the reason why what Amanda studies and what we've tried to understand the neural basis of is so important for autism is that it's not the very high-level complex thinking that's gone awry, but rather these very basic social perception action understanding that provide the fundamental building blocks for more sophisticated things like theory of mind that are actually going awry. Okay, so now moving into we've got a good developmental understanding of behavioral development of social functioning. Amanda's provided that. Myself and many other scientists, Jean DeSetti in particular at Chicago, Jessica Somerville, who became a neuroscientist after getting her PhD with Amanda, we've all gone on to identify the neural circuitry. And some of us with an interest in autism have begun to try to nail down what is it that's different in autism and how does that link on to symptomatology. And so what's really cool about these systems, the social perception system in the brain, behaviorally that Amanda studies, is that you can tap into it just presenting any form of biological motion. So pretty much anything anyone does, your system is constantly making predictions about that action. Again, you can't turn it off. So really, you just present biological versus scrambled motion, which is great for somebody like me that wants a very simple experiment that I can do in this big magnet that's measuring people's brain activity. So person playing patty cake, scrambled version of person playing patty cake. And what we've done in terms of looking at how this relates to autism is to identify the neural circuitry that's affected in autism. Here, without going into too much detail on this, what you're seeing in red or orange is the regions that are responding differentially in individuals with autism. We call this state activity. The state of having autism is reflected in this picture of the brain during the perception of biological versus scrambled biological motion. So we have a sense of an underlying neural correlate. And we and others have mapped these types of neural correlates, these biomarkers, onto behavior, and in some cases we've shown that even in the absence of autism, they relate to the genetic risk of developing autism, and that they relate to the social functioning in the real world. This is the signal from the brain of processing biological versus scrambled motion. This is something called the social responsiveness scale, which is a very elegant measure of social functioning, and I'm simply showing that there's a strong correlation to how you're acting in the world, your social adeptness, as measured by people observing you, is related to how your social brain is functioning. And so given that link to autistic symptomatology, I would argue then that you can then move forward and begin to try to use those markers as the targets for well-informed treatments, and again, thinking about what might be non-obvious. Now, the other thing that is important here is I've shown you work from older children and adults with and without autism. What's critically important is to try to understand the developmental trajectories when they're happening. And what Amanda's provided is a beautiful roadmap of when we should be looking for thinking about the development of social understanding and action understanding in particular in autism. And so we've had to develop techniques. This is an optode array that allows you to look at using near-infrared light. Cortical activity in the infant brain works particularly well in infants because they have very little hair and their skull is still forming, and so you can beautifully image neural activity with this technique. This is a baby simply wearing one of these optode nets and sitting in the parent's lap, in this case looking at biological and scrambled motion. And what's exciting about this is that even at 3 months of age, you see in low-risk infants who don't have a sibling with autism, you see a beautiful differentiation between biological motion shown in blue and the scrambled version of that, so non-biological motion. And it's specific to the right hemisphere in this posterior temporal lobe region. So we get a sense of when in development we begin to see this differentiation. It maps on very nicely to the behavioral work. But now we have a neural signature that we can use to try to inform our treatments and try to inform and be used as a target for a treatment. And it's important to say that high-risk infants that have a sibling with autism, fail to show this differentiation. And what I think is important to point out is this is a sample of 12 low-risk and 12 high-risk babies. Chances are none of these babies are going to develop autism, right? Statistically, we might get one with this type of sample size. But yet, the underlying neural signature is reflecting the genetic risk, even though probably the behavioral outcome won't emerge. So how will these babies avoid having autism when they have a neural system that's already showing such strong signs of dysfunction? And that, I think, is a developmental question that could lead to a great deal of understanding about how to design, in particular, behavioral treatments. What experiences allow an infant to develop compensatory mechanisms that allow them to avoid the autism outcome? Now, in this sort of path forward that I mentioned, I argued that we can begin to develop interventions. I want to show you one drug compound intervention and then one behavioral intervention quickly. The first is the drug compound. So we recently conducted a study where we administered intranasal oxytocin. And we chose oxytocin because of its importance as a molecule in many aspects of social function. based on that basic research, we thought it might well be involved in the development of this action system. And we used a task that we simply asked subjects, judge the emotion from the eyes, so a very social judgment. Control task that was name the type of car and the headlights. So surface features very similar, task demands are similar. One's a social task, one's a non-social task. And actually, we just found out this is accepted in the proceedings of the National Academy. We found out this morning, and my student, Ilanique Gordon, was just also found out she has a job at Bar Ilan University in Israel. So lots of good news today. This is the differentiation between the social brain on oxytocin versus placebo. This was a double-blind, placebo-controlled study of intranasal oxytocin in 18 participants. And so what was really interesting about this data, and it relates to points that Amanda brought up about what the infants attend to. How do they know what to attend to in order to derive the structure that's there in the world? And how even their own actions, how do they know which actions to attend to, or to attend to their own actions on the world? And what we found was a differential effect of oxytocin. There's really two effects. One was to increase the response to the social stimulus, and another was to decrease the response to the non-social stimulus. So there was a tuning. It wasn't just a main effect on, process more strongly the social stimulus. It also pared down the response to the non-social stimulus. Highly specific effects. In addition, that's came out very weird. I'll just tell you without reference to the figure. It reduced the noise specifically to the social stimulus. So it increased the signal value of the social stimulus and had selective effects depending on which regions of the brain you looked at. So again, highlighting that autism is not a whole brain complex information processing disorder. If it's a synaptopathology, it's not a synaptopathology everywhere. It has a specific timing and a specific places in the brain that are most affected. And that becomes the developmental question. And it's why this basic developmental psychology work is so important in order to tell us something about when and where we should look in order to really start to pull apart this puzzle. Now, the last thing I want to tell you about, I hope will highlight the plasticity of autism. And so we tend to think of early intervention. If we sort of take the obvious route, we would think, well, you would want to identify as early as possible and then alter the developmental trajectory. And if you don't catch it really, really early, then there's probably not much you can do behaviorally. And so I would argue that's incorrect. So what we have here is a behavioral intervention, pivotal response training. And what I like about pivotal response training is that it targets these pivotal intention understanding behaviors and structures, mechanisms, and we thought presumably the brain structures as well, that allow individuals to understand others' intentions and therefore begin to broadly move their ability to derive important information about the social world. And so we implemented this in a 16-week behavioral intervention in children that were 4 to 6 years of age. And this is the primary outcome measure. This was against a wait list, an active wait list control, where we provide some respite, some free play with the children, but we weren't providing, so we showed up just as often, but we weren't providing pivotal response training. This is the change in the social responsiveness scale. These add up to this. This is the total change, showing a nice behavioral improvement in these kids. And this is known. This treatment is one of the empirically supported treatments. But we looked at what changes in the brain and in response to social versus non-social stimuli. And what we're finding is that the very circuitry that's involved in intention understanding is the circuitry that's connected with behavioral change that you see when you use something like pivotal response training, and it works for the kids. And so, again, it's not changing the whole brain. It's changing specific components of the brain. They're linked to something that we already understand a lot about in terms of the early behavioral literature. And therefore, it sort of raises the question of, do we have this path forward at a neural systems level where we can begin to implement things that we know work and understand their effects, first on neural circuitry, but also perhaps gene expression. And if we're seeing neural circuitry changes, there have to also be associated genetic expression changes. And so understanding that path, I think you can then reverse engineer and start looking at genetic pathways that would be of interest. And then again, looking at these non-obvious, I'm dying to run back to the lab and do a sticky Mittens study on these infants, because it's the type of non-obvious experience that those of us that see kids with autism every day wouldn't think of. Oh, well, let's manipulate that. Why? But you've shown why. And I think that this idea of non-obvious experiences is going to be very, very powerful. And so, and that relates to my last point, which is, can we begin to identify at-risk children, intervene through very creative developmental psychology and social neuroscience informed treatments that will, sticky mittens will do no harm. And then see if we can actually alter developmental trajectories in these brain structures as neural markers, so that even when we don't see, so what I'm saying is, eliminate the autism from appearing. Well, how do you know you eliminated the autism from appearing instead of just got lucky? Well, if you can look at the underlying neural circuitry, which you've now shown very strongly correlates with the development of autism, we've done that. Can you now see that by altering the trajectory of those neural circuitry, there's a greater percentage of infants who no longer develop autism? That's the type of work that I think that is inspired by Amanda's findings, where we know with great certainty, we have a great sense of the underlying growth charts of what should happen, and now we can use these very sensitive experimental measures to find out what happens as a result of intervention. So I want to stop there and just, the work the data that I showed you is supported in large part by the Simons Foundation and these other sources as well. So, and thank you very much. And thank you, Amanda.